What happens when you need Google-level search plus support for wildcards? Design, add, and search words data structure is a Pattern Mastery 100 favorite and a must-know at top tech interviews, blending try design with recursive search logic. Over 35% of candidates fumble the wildcard or get stuck on recursion. Let's make sure you're ready to shine. Let's break down design, add, and search words data structure using the basic approach, step by step, to cover all the nuances of both try operations and pattern matching. Build a data structure that supports. Add word adds a word into the data structure. Search word returns true if the word exists. Where can represent any letter. Wildcard input/output supports any lowercase word. Search may include. As a wildcard, needs to handle both standard word lookups and pattern matches efficiently. Imagine a code search tool that must find variables or function names with partial information, like foo.bar matching foobar and foobar. An interviewer might ask, how would you design a dictionary with fast wildcard search for autocomplete or spell checking? What's tricky? Standard try can handle prefix search, but now you need to support period wildcards, which can match any character at a position. Recursive, DFS, search is required. When you hit period, you must explore all child nodes at that level. Must distinguish between matching a word's full length, is_end, and just matching a prefix. Think step by step. Use a try node class, children, letter node, and is_end boolean. Add word. Same as regular try insert, follow/create nodes for each letter, set is_end at the end. Search, word. Walk down the try for each character. If current char is not period, follow the child node as usual. If current char is period, recursively try all children at this node. At the end of the word, return true only if the is_end is set. Use recursion to handle branching at period efficiently. Let's clarify. The wildcard search will branch out at each period, but prunes quickly if a child doesn't exist. The structure is the same as a standard try, but search must explore all possible matching paths when wildcards are present. Edge cases. Multiple wildcards, for example, empty string, should only match if empty word was added. Search for word longer than any added, should return false try node. Children, dictionary for each letter is_end, boolean word dictionary. Root node, try node, add word, standard insert search word, recursive DFS with branching on. Now let's implement the length bucket approach, grouping words by size so searches only compare against candidates with the same length. Data structure setup, we store words in buckets based on their length. This way, when searching, we only compare against words of the same size, making things more efficient than scanning everything. Add word method, we get the bucket for this word length, creating it if needed, and then simply add the word to that bucket. This makes insertion extremely fast. Search method, we determine the length of the search word. This tells us exactly which bucket to check. If no bucket exists for this length, there's no way the word, or even a wildcard version of it, is in the dictionary. Case 1, no wildcards. If the search word has no dots, we simply do a normal lookup in the bucket. This is a fast direct comparison. Case 2, word contains wildcards. We loop through each candidate word in the appropriate bucket. All of them have the same length. We assume the candidate matches until proven otherwise. We compare each character of the query to each character of the candidate. If the query character is not a dot and doesn't match the candidate character, this candidate cannot be a match. We mark it as not matching and break out early to avoid unnecessary comparisons. If the candidate survived all character checks, it means we found a valid match, so return true. No matches. If none of the same length candidates match the wildcard pattern, we return false. And that's how this algorithm works. It first groups words by length for fast narrowing, then compares characters carefully to allow dots to match anything. Efficient, simple, and elegant. Let's test our word dictionary with these inserts and searches. We add 3 words and then query both exact matches and wildcard patterns. Search pad, false because pad was never added. Search bad, true because it matches exactly. Search, add, true since any first letter plus add matches bad, dad, or mad. Search b, true because bad fits the pattern. The output matches the expected results perfectly. So, our implementation is correct. The dictionary handles both normal and wildcard searches as intended. Now let's implement the try plus DFS method, exploring character paths and handling wildcard searches efficiently using depth-first traversal. Try node definition. Each try node holds up to 26 possible children, 1 for each lowercase letter. If a child is missing, its slot stays null. This gives us constant time indexing. This marks whether a node represents the end of a valid word. It's how we distinguish full words from mere prefixes. Word dictionary setup: we create a root node for our try. All words begin their paths from this root. Add word method: we begin insertion at the root node. We loop through each character of the new word. We convert the character into a zero-based index. For example, C maps to 2. If the path for this character doesn't exist yet, we create a new try node, and then we walk deeper into the try along this path. When we finish processing all characters, we mark the final node as the end of a complete word. Search method. To support wildcard searching, we delegate the work to a DFS helper. We start at index 0 of the word from the root node. DFS helper method. If we've processed every character, we return whether we landed on a true end of word node. This decides whether the search word is valid. We read the current character from the pattern. Case 1. Wildcard. If the character is a dot, it can match any letter. So we must explore all 26 possible child paths. We check each child node one by one. If a child exists and continuing DFS from that child produces a match, we can return true immediately. If no branch produced a match, then this wildcard path fails. Case 2. Normal character. We find the child corresponding to this letter. If the child exists, we recursively search deeper. If it doesn't exist, the word cannot match. And that's how this algorithm works. It first builds a try for fast prefix storage, then uses DFS to explore all valid paths, including branching paths for wildcard characters. Efficient, simple, and elegant. Let's test our word dictionary using these operations. We add 3 words, then run searches, including wildcard queries. Search pad, false because pad was never added. Search bad, true since it matches exactly. Search add, true because any first letter followed by add matches the stored words. Search b, true since bad fits the pattern. And that's exactly what the program outputs, matching the expected results. So, our implementation is correct. It handles both exact and wildcard searches just as intended. Wildcard search at Google speed isn't magic, it's design. In this problem, we blended a try with smart recursion so pattern matches with feel instant and reliable. Let's do a recap. The goal was simple. Build a structure that can add words and search them, where can stand in for any single letter. Conceptually, we're storing shared prefixes once and answering both exact and wildcard queries in OL time. The tricky part is the wildcard. A plain try handles exact matches and prefixes, but forces branching. We solve this by exploring all children at the wildcard position, while still enforcing that a full word must end at the final node, not just a prefix. We organized everything around a try node with character links and an is_end flag. The plan: add word walks or creates nodes per character, then marks the end. Search scans character by character. On letters we follow the link, and on. We recursively try each child. Success only counts if we land on a node marked as a complete word. We followed that blueprint exactly. Standard insert for adds, depth first branching on. For searches, and kept the logic tight to avoid unnecessary paths. The solution ran cleanly without errors. We verified on Leetcode. After adding bad, dad, mad, searches like pad returned false, bad returned true, and patterns such as add and b returned true. Edge cases behaved as expected, and tests passed. The takeaway: combine try sharing for prefixes with precise DFS at wildcard spots. Respect the is_end check, branch only when you see, and you'll get fast, correct pattern matches every time.